right?
Green computing in HPC, sir. Yes, sir. Yes, sir.
Yeah. So good afternoon, all of you. So I can start, right?
Yes, sir. Yes, sir. Good afternoon, sir. Please start, sir.
Yeah. So today the discussion is towards the green computing in HPC. Okay. So far we heard about in the last class about the performance and then the mix of CPU, GPU, the hybrid nature, and various memories. Okay. And then we also spoke about some of the subsystems in the IT side, like InfiniBand, that is a interconnect. Then you need a storage which is associated with this high performance storage like parallel file system. So we talked about ecosystems like compilers, libraries, application software, system software, all that. Today's session is basically we are talking about how to achieve a green, what is meant by green computing, and then how to achieve it, and what are the subsystems which are actually part of the green computing. Okay. So this is the outline, the overview of the data center. See, to know about this green computing, the green computing is basically associated with majorly three components. One is the raw power, like say what is the power you are giving to the system, and the second one is what is the cooling required, okay, to remove that heat, whatever is heat generated, because you are giving a power to the system is going to generate some heat, and you have to remove that heat so that the system is efficiently working. Okay, otherwise the system may conk off, or it may hang up, or some nasty things may happen. So you have to remove that heat. Okay, so the heat removal, there are so many techniques. So today's discussion basically goes into the various techniques in the data center with respect to the heat removal, and what are the equipments we talk about, which are actually to run a particular HPC system. You need to create a data center kind of environment. I am talking about specifically large systems. Okay, so whenever you are creating this kind of a data center, big data centers, the difference between the traditional data centers and this HPC data centers is totally different. Why it is different is the look and feel is same, the infrastructure is same, the cooling is same, the power supply equipment is same. You need a transformer and all that. Whatever is required to run a data center, you need same thing for the HPC. But the difference is, what happens is whenever you are running a particular benchmarking kind of things on the HPC or a bigger job on the HPC system, all the systems are fully loaded, and the last mile drop of this particular system's performance has been taken out. Okay, in that process, what happens? You are utilizing all the memories, you are utilizing the clock speeds of entire CPU, you are ensuring that the system is fully loaded with all the course functional, whatever it can give the best performance. So in that process, what happens? The heat generates also, a lot of heat it generates. Whereas in the traditional data center, what happens is web host, some servers are for web hosting, some servers are for the database applications, some servers are front-end application servers. What happens is the load is not, all are not 100% loaded all the time. So there is a big variation in the overall, the heat generated by these systems. So that is the difference between the HPC data center or a traditional data center. But otherwise, the infrastructure wise, it is same. So it is very important to know that what are the equipment, and why that equipment I have to know. I will come to know in the subsequent slides. And the DC cooling techniques, and then CPU server cooling techniques. Okay, so far we are talking about, like say, we understand room cooling, we understand rack cooling. Okay, the rack is cooled because we want to ensure that the servers inside the rack are, they are cooled up. Okay, now the next thing is, the next session I'll talk about this overview of the green 500 supercomputers. What is the overview worldwide? What is the scenario? And then how you are going to do this power management and power versus performance. Okay, so that is what is the crux of it, the green 500. What is the performance you are getting and what is the energy you are spending. These two are the crucial things to understand what is a green 500. Okay, and then I'll talk about a few things about the green 500 exercise and the benchmarking. Okay, so this is the outline. So this is the typical data center. If you see the Google data center, which is distributed across like say 40 locations and 19 major centers, and this is the server farms. So what happens in the Google, you know, a lot of applications are running. Google is offering mail, Google is offering some, you know, map service, Google is offering some databases, Google is also hosting some of the companies hosting infrastructure, like say it can be a web hosting or a particular application hosting. So they are offering multiple types of, you know, the loads are also different, and they're offering, but it looks like something like that, a typical data center. And this is the Facebook data center. You can see that, you know, a lot of like say 2 lakhs, we are talking about something around like say, you know, 2 lakh servers or 20,000 servers at each of the floor. There will be multiple floors like that. Okay. And you know, millions of activities per day which are happening on that across some 12 data centers. Okay. Now coming back to this, we are talking about you're able to see the top heading also in the presentation.
Data center, non-IT infrastructure.
Yeah, you're able to see that, right?
Yes, sir. Yes, sir.
Yeah. Okay. So when you do the design consideration, like say for making a data center, around the data center, you need some of the, you know, back-end power infrastructure, right? The power infrastructure also depends on the data center type what we talk about. In a general data center, what happens if you go to talk to any of the data centers like you know, the Google or a Facebook or something, they talk about a tier 4, tier 5 kind of data centers. Okay. So that is a different topic. What is a tier 1, tier 2, tier 3, tier 4, tier 5? So that is basically, you know, the tier 5 is the highest and the tier 1 is the lowest. Tier 1 means no redundancy. Tier 2 is redundancy up to some extent. That is n plus 1. It is not n plus n. Tier 3 we talk about n plus n. And tier 4 is like say talking about a different sources, power sources. At a different power sources means it's not just two connections. The power source, what is the originating? Like say for example, one source is coming from some atomic energy, another source is coming from some other, you know, solar or some other or a wind or a water kind of thing. Okay, so they talk about that level of, you know, the redundancy with respect to each and every component with respect to the IT and as well as the non-IT infrastructures. Okay, so here in the HPC, usually people doesn't go for that kind of, you know, tier 4s, tier 5s because the infrastructure cost is huge, and you know, we are not even if you are running a mission critical, it is not that mission critical that if something happens for a minute or something goes down for 5 minutes, it's not that entire thing is down. So what we ensure it, like say for example, you are having like say you know 200 nodes. Okay, even if like say some nodes are conk off like say 10 or 5 servers, the job running all that is going to affect but not the entire system. What is the crucial here? What is the time taken to restore it? Majorly for me is that, you know, the storage. If storage is not shut down properly, then it takes, you know, hours and hours to recheck the file system, the integrity of the file system, and make it available to the users. Okay, so that is the only crucial part for me, and remaining things are, you know, the job may go off, but you can rerun the job. So that is why we don't go for a, you know, n plus n kind of thing, but we will ensure that n plus 1 is there. Okay, so you have a transformer and you have a diesel generator, and then you have the UPS with battery, and then there is a synchronization panel. So this is the one is a synchronization panel. Okay, and this is the DG set and UPS, and then this is the transformer. This is the electrical subsystem I am talking about. The job of the synchronization panel is I can have multiple sources connected to the synchronization panel. Like say one is a DG set, another is a transformer, and I can have one more transformer. What this synchronization panel does is that it will automatically switch to the next source in case of if one source is not available. Okay, and the battery associated with the UPS usually will not be taken more than 20-30 minutes backup, because any DG set automatically which is going to start, which is attached to the synchronization panel, is going to come up in less than a minute. Okay, and it takes another minute to take entire load. So that is why I don't need a battery backup of huge backups, because like say in 20 minutes if DG set is not going to come up and if another source is not going to come up, then automatic I have the, like say system administrators will have their own way of shutting down the systems. Okay, because ultimately it's a cost, everything is cost. Now coming to this overall look how it looks like, in the non-IT infrastructure, you see, if this is the entire thing is a the data center platform. Okay, now what are all I should consider here? There are a lot of factors which are need to be considered. Okay, one is the server out temperature, and what is the inlet temperature I am giving, what is the temperature I am giving, what is the outlet I am giving, what is the fan speed at which the air is blowing from the bottom if it is a bottom level cooling, and what is the delta? What is the delta means? What is the variation? Like say for example, if my input temperature is for example 18 degrees. Okay. Now what happens after heating? Okay, the outlet like say the outlet temperature is around like say 24. Right? There is a 6 degree change in that. Now the 24 I have to able to cool it back and then feed that 18 back. If I am not able to give that 18 back, if I give, what happens even if it is 18.1, what happens after some time? This becomes a cumulative effect. 18.1 becomes 18.2, then it goes to 19, then it goes to 20, then it goes to 21. Now what is happening? Every time that 6 degree, what is the delta change is there, that 6 degrees are adding to that outlet temperature, and my input temperature will become, what happens? 30 degrees. So what we saw in half an hour, the delta T changes so much. If you are not able to effectively cool it, you cannot even touch the handle of the door of the data center. So it is becoming like 50 degrees, 60 degrees kind of temperature. So that is why the delta T is very, very important to ensure that whatever outlet temperature which is coming out, that air temperature, I should able to cool it down, and my input temperature should not vary. Okay. Now, what is that equation here? DCIM. So I just referred as something called DCIM. That is a data center infrastructure management. Okay. What it talks about is IT equipment power versus total facility power. What is the total facility power? Hello? Any question? Okay.
డాటా సెంటర్లు హై పర్ఫార్మెన్స్ కంప్యూటర్ అని కొంచెం కొంచెం చెప్తున్నాడు వీళ్ళు అయితే.
హలో
తెలియదు మనకు సరిగ్గా.
హలో హలో
సార్
గుడ్ ఆఫ్టర్నూన్ గుడ్ ఈవినింగ్ తప్ప వేరే ఏం పెడుతుంది ఇలా.
హలో
నో సార్, నో సార్, యూ ప్లీజ్ ప్రొసీడ్ సార్.
Okay. So, what is happening here is that IT equipment power is very less, and then you have to see the total facility power. Total facility power is actually depends on what are the losses with respect to the cooling and with respect to your electrical subsystem. Okay. And the next terminology, what we call it as inverse of the DCIM, that is the PUE, power usage effectiveness. What it does is, it's an inverse of the DCIM, that is total facility power, means I need like say 1 megawatt is the power required to run the facility, out of which maybe the IT equipment power is only like say around 600 kW. Okay. So total facility maybe the 400 kW is actually is coming the consumed by the what you call the losses in the electrical subsystem and the AC subsystem to run the cooling. to provide the cooling. Okay. Now these are the different various techniques. How do you cool a particular HPC system or in any of the data center? So one is like say the computer cores are used. You know the density is more. Now what is happening is the heat. Generally, what happens is in a normal data center, the heat load per rack is not going to cross around 5 to 7 kilowatt. But because of the high density of this HPC nodes, the nature, what is happening is the temperatures are going up to 30 kilowatt per rack. Okay. Now, when it goes to that much high temperature, 30 kilowatt per rack, then what happens is you cannot mix this hot air and cold air easily. What happens if you start mixing it, then the efficiency will come down. So what happens, they are going to, ensure that there is a chamber made. If you can see this on top of the rack, the chambers are made such a way that the hot air is always lighter. It is escaping to the top and then it is sucked by the PAC pressure air conditions and then the cold air is coming from the bottom. That is how the airflow is designed. Okay. Only thing is these chambers are made to ensure that the hot air is not mixing with the cold air. Now coming to this room oriented cooling. So what is that approach here? Here we are talking about, then the first one what we are talking about is bottom level cooling where the cold air is coming from the bottom and the hot air is coming out from the top, the chamber what is made for that. And then it goes through the duct and then the duct is again feed it to the pressure air condition and the pressure air condition is taking that heat, reducing it and then again giving the cold air. The pressure air condition may be running in the back end with a gas, okay, or chiller. So that is a different story altogether. So whatever the mechanism, it is going to reduce the heat and then give back to that. What are the problem associated with this cooling? We'll discuss in the later. Okay, and this is the cooling. If you take about the room perspective, if you see that what they have done, there are two techniques here. One is either I'll do a containment to the cold air, or I'll do a containment of the hot air. Okay, so what we saw in the previous one and this one is the hot air is in the previous one the hot air is contained. That means it is given a separate chamber to escape and so that it is not mixing with this. And whereas in this case, if you see that I can do a cold air containment, this is hanging one edge over the other one. Okay. So the bottom level, the cold air is coming and then the hot air is, contained in one case. In the other case, what happens, I do a cold air containment and I'll ensure that the hot air is mixed in the room. So both are having its own advantage and disadvantage. When you allow the hot air to mix it to the room, the entire room, what happens, you are getting an expansion. The air is getting expanded, so the cooling will be quicker. Okay. It is not, constructed to a particular area, confined to a particular area. Whereas if you do the cold containment, what is the advantage of that is that in case of even if power goes for a minute, by the time the DG set comes up, this cold air containment is such a way that the fans are still able to, see some cold air for sucking from the front and then discharging from the bottom, back. That is how the servers are designed. Okay. Now this is the typical, if you see that, how do you have to be very careful in plotting and understanding this, the bottom level cooling, whatever it is. So you see the variation in the temperatures. You can see that, the top, somewhere the top is, 30 degrees. Okay. And the bottom temperature, the middle, the temperatures on the bottom is also high and the temperatures on the top is also high. Okay. In between it is fine. Why it is happening is the nature of the air. What happens when you are giving a cold air from the bottom, you have to increase the CFM. That is a cubic feet per meter. That is the speed at which the air is thrown from the bottom. Now what happens? Each server is having a front end fans which will suck the cold air inside, and then the hot air is discharged from the back. In this mechanism, what happens? If we increase the CFM, the cold air through speed of the velocity of this cold air, what happens? The fans are not able to suck it because the fans are not able to suck that particular speed. So if we increase the speed, what happens? The fans are not able to suck. So the nodes which are kept in the down are not getting proper cooling. And by the time it goes to the middle, the velocity is reduced. So the middle servers are able to suck the cold air effectively. Okay, and the cooling is perfect. When you go to the top of the rack, what happens again? The velocity is reduced so much that it is not getting enough air to cool the node on the top of it. So that is what we have seen variation when you do the, this cooling in the bottom level cooling. Okay. Now to overcome that, so there is another technology which is like what we do is we'll have this placement of this. You can see this, the blue ones. Okay. They are nothing but the AC units. These are the air conditioning units. There is a PUC, pressure air conditions. This technique is called row based cooling. What I am doing is putting the air from the bottom. What this does is each of this particular AC unit hang the plops to throw the air from both the sides, like from top to the bottom. Like say if you take a rack, typical rack, which is of a 42U size height. So it is throwing air from top to the bottom in both ways. So now what happens? Each server is getting equal amount of the air, so that it can effectively cool it. So that is how this particular ACs are placed in between the racks. Okay, and it looks like a rack. It exactly the dimensions of the rack, but it is comparatively the width is smaller compared to the rack width. Rack widths are different. Definitely the rack sizes are 600 mm by 1200 mm. That is a 600 mm is the width and 1200 mm is the depth. Or for the some of the storages, it will be 800 mm width and the like say 1200 mm depth. So this particular AC units are like say 300 mm width and then 1200 mm depth. So it is exactly sits like a rack in between these racks, and then it is throwing the air from top to the bottom on both sideways, so that each server is able to get the proper air. So what is the advantage? You don't need a raised floor because you don't need a bottom level air coming to the top. So you don't need to create any chamber for the cold air. So it is on the top already along with the rack, just side by the rack. So I don't need a false floor, this false floor or a raised floor. And no additional space required for outside units. Like say I don't need additional fans or anything to be used there. And lower capital expense because no piping, less power consumption, because I don't need to do any channeling or piping or anything, because only these units are there which is giving the cold air. So airflow paths are shorter. What is the principle here? The principle is the more whatever the heat you are generating, the more you go closer to the heat source, you can cool it easily. Okay, instead of cooling outside, if I'm throwing an air, it is not exactly starting at the where the heat is generated. The heat source is generated at some other place. The cold air is at some other place. So after some mixing or some flow, and there is a gap between that where the heat is generated and where the cold air is coming. So if you go nearer to the heat source, you should be able to cool it effectively. So that is what is the advantage of this. Only the disadvantage here is that you are losing some space because you are placing them in between the racks, these AC units. Now the next type of cooling is a rack level. Now we have seen it initially, the entire data center level cooling from the bottom. Then now we are seeing the rack level. After that we have seen row level cooling. The previous one is a row level. So this is the entire row is being cooled. Okay. And the next one what I talked about is a rack level cooling. So within the rack I am throwing the cold air and I am removing the hot air from the front. And again this hot air is given back. It is happening within the rack only. The hot air is coming and it is getting cooled and then again it is fed it to the system. So what is happening here is the PAC, the pressure air conditioning is within the rack itself. The cooling is happening within the rack. So everything is confined to the rack. So the the CRAC units are associated with the rack and they are dedicated to the one or two racks and it's a closed chamber. Okay, that is why what happens, the distance what this hot air need to travel is less and it is within the system, so it is not having any additional losses and it is not mixing up the air, either a cold air or a hot air. So what is happening is it is more effective. That is the advantage of it. So the paths are shorter. Okay. So and room temperature, there is no variation irrespective of the room temperature. Whatever the room temperature, overall room temperature, it is not affecting your cooling here. Okay. And highest power density I can go up to 50 kilowatt per rack. So initially what we talked about the first one, bottom level cooling, I am only saying that about 7 to 10 kilowatt, and the next level when I come to the row level I am able to say that 30 kilowatt kind of thing, and in this within the rack level cooling I can go up to 50 kilowatt per rack, but I can achieve much more. We'll see the less on next slides how we can achieve that. Okay. So now we are coming to the next kind of thing, this hybrid. Doing is I am doing a room based cooling, that is a bottom level cooling. I am doing a rack oriented cooling. I am also doing a row oriented cooling. Why I am doing all these things in this? Each is cooling technique is having some advantage and disadvantage. The IT equipment also. For example, you want to okay, or you want to cool a tape library, or you want to cool some equipment, like say the network equipment. Okay, so what happens is depends on the equipment type, the efficiency of the the if you go to the network side, the network switches, whatever the heat generation is very less compared to a server what it is generating, or a GPU server what it is generating the heat. So there I don't need to waste my other techniques because I can get away with the entire rack row level cooling or a bottom level cooling. So it depends on what is that particular row. That particular row is having, like say if InfiniBand, Ethernet, management, all my networks are in one row. Okay, then I'll say that okay, this row I need not, like say tape library is also in that row. I'll say that this doesn't need more than 5 kilowatt or a 7 kilowatt kind of cooling. I don't need to go for a 50 kilowatt or a 100 kilowatt kind of cooling. So it depends on what is that heat generated. If you compare the storage heat, whatever it is generating compared to your GPU cluster or GPU nodes, it is less. So there I can even go for a row level cooling. Okay, but when it comes to this particular HPC, the more you go closer to the heat source, you can easily cool it. So that is the hybrid model. Now you see that what is that percentage, how it is getting cooled up. Okay, if you see that if you take that 100% is your the usable capacity, okay, and versus your density per rack, okay, you see which is flaring better. Okay, so if you see that the row oriented cooling is, like say initially it is poor, but overall it is performing better, and whereas room oriented cooling it is actually decreasing, or the this one when the heat is getting increased, then the efficiency will come down. And whereas in the rack level rack oriented cooling it is stable. because it doesn't matter what you are running, it is able to cool it within the rack. So it is much more stable and effective. So now the next level. Why don't we go, why we are talking about a rack level cooling, row level cooling. Okay. Now let us talk about the CPU level cooling. Okay. When we say that everybody knows that the CPU is the one which is actually generates a lot of heat. It dims. So these are the major heat sources of any of the server. Now, if you say this, see this particular image, you can see these CPUs. Like say this is a AICTE CPU motherboard, for example. You can see this. The CPUs are having this inlet and outlet. The copper is having an inlet and an outlet. So if I am circulating a, the car, how you do cool it? You circulate the coolant, right? Similarly, I have an option to run a coolant, or I can run it directly a water to remove the heat. So what I am doing here, we are actually removing the heat where it is generated. So it is much more efficient. Now this is the server level cooling. Now we have seen that CPU how it is, and similar same thing is extended to the server. If you see the server level cooling, now I'll extend my the cooling techniques to the memory DIMMs. Okay, I can do a contact based. I can remove the heat either through contact. Okay, and this contact, whatever I use a heat plate, and the plate is actually circulating a coolant or a water. Now what is happening? It is removing the heat. Whatever the heat is generated, it is removing the heat, and you have a water inlet and you have a water outlet. And these are connected to your backend, the chiller, which will ensure the, the PAC to the chiller, which will ensure the temperature of this, the water inlet is maintained. Okay, even there is a variation in the outlet. Okay, so that is how the things are designed. So this is, the previous one is called as a DCLC, we call it as a direct chip level cooling. And this is the server level cooling. The servers are designed such a way that it is having an inlet and outlet, and the water can circulate within this particular heat sinks, and thereby removing the heat. Now we are again talking about the PUE, because the PUE and the DCM are the crucial things for any of the, if you talk about efficiency of a particular HPC system when it comes to the green 500. Okay, so the efficiency means what? For example, with less power I can do more work, or with, that is the efficiency here. Okay, so that is why we are measuring that what is the losses and what is the total energy we are spending on that, and what is the efficiency of the system, what I am getting it. So now I'll see what is the performance versus my consumption. Okay, that is how we are talking about it. P means total facility energy by IT equipment energy. That gives me the power factor. Like say if it is unity, then your thing is excellent. That means you are spending very minimal for the cooling. Okay, the energy losses are very minimal. So usually people go talk about that ideal is 1.0, but it never happens. So it will be around 0.8 to 0.9 kind of things. Now come to the green 500, okay, and the top 500. Hello, any question? Any question?
Participants, please post any questions in the chat box or directly ask the sir. No sir, you can proceed.
Okay. So here if you see that, you can see this top 500 rank, and you can see the green 500 rank, and you see the company, what is the country, and what are the CPU cores, and what are the accelerators, like say GPU cores, you call it as accelerator, GPU coprocessor, whatever it is, and you see the max, R peak, and the power consumption, and energy efficiency, and the processor technology, and the coprocessor or accelerator or a GPU technology, and cores per socket and the interconnect. So I have given the entire overview of the particular HPC system. If you see the top 500, okay, and then compare it with the, green 500, how it is performing when it comes to the power efficiency. So if you take that EL capital, this is the one which is a number one system. Okay. This is the number one system, exaflop system. And it is hang, you see that how many cores it is hang. It's hang around, pardon? So you see the number of cores and the number of GPUs what it is using, right? And the performance. So it is a theoretically is 2.7 exa, and what is the practically what it is giving? This is the R peak is a theoretical performance, and R max is the performance what you got after running the benchmark. So you are getting around 1.74 exaflops out of 2.74 exaflops. This is the theoretical. So theoretical means if I calculate the number of, the processors and the, GPUs into their clock speeds, into their floating point operations, that gives me the performance. And this performance is usually measured by running a HPL. Okay? Benchmarking, HPL benchmark. Pardon? Hello?
No, sir, he proceeds that it is noise. Sir.
Okay. Okay. So now the number one does not mean that the number one performance with respect to the the performance of the system doesn't mean that it is qualified as a number one on the green 500, because if you see the energy losses, the performance is coming around 58.89. That is the performance it is giving when you see the power efficiency. Okay. So it is, the power in kW is very, very, high. When you see the performance is only 58.8 line. That is what is the gigaflops per watt. Per watt it is able to give me 58.8 line gigaflops per each watt. That is the performance of the system. Okay, that is why it is ranked as green 500 it is ranked as 18. And when you go to this, the supercomputer which is ranked as 222, okay, JD. So what it is giving? It is giving around 72.73 gigaflops per a particular watt. That means this is more and more efficient. The efficiency is more. Okay. The efficiency is more, that is why it is ranked as number one. So you see the difference between this number of cores are here 24 and here the number of cores are 72. Okay, and you see here this what it is using is a AMD, and whereas here what it is using is NVIDIA. So every component whatever you are using is going to contribute, okay, to either a higher side or a lower side, depends on the what it is performing. Okay, so performance per watt is measured to decide which is the number one supercomputer in the green 500. And whereas top 500 doesn't talk about power performance, it only talks about the system performance. Okay, the system performance is exaflop, that is the highest, so it is ranked number one. But when it comes to the performance per watt, it is at a 18th position. I think this is understood, right? This slide. Now you see that in the pictorial representation, you can see this. The number one is the 222. Okay. And you can see this. This is the rank. If you go to the 20th rank is like, say the rank is varying. This is the top 500 rank. Now this is the top 500. In the top 500, this is 369 ranking, but whereas it is ranked 8th in the green 500, because the efficiency what it is giving, performance per watt, is dictating whether it should be in the top it should be in the top in the green 500 or not. That is how it is decided. Okay, this is the energy efficiency is always measured in the gigaflops or what. Okay, so this is the facility layout. Why I am talking about this facility layout is very important. I am giving an example of UR2 because this will tell us how do you know measure this particular the performance and the power consumption, and how do you draw this particular relation to ensure that you are getting the green violet ranking. Okay, so if you see this, this is the Param UR2 facility of CTAC, and you have this primary power source. You can say this is like a transformer, and you have a genset 1 and genset 2, and you have this synchronization panel for synchronizing the source between this your transformer and the DG sets, and you have the UPS. Okay, UPS in and UPS out. This is the 2 in number, that is n plus 1 n here, and DG sets also here n plus n. Okay, and the UPS output is here, and this output is actually connecting to each of the rack. And these packs, the the never ever the ACs are not connected on a UPS, because the ACs are a variable loads, and variable loads are not connected onto the UPS. They'll be always connected on the raw side. So that is why power goes, you have to ensure that by the time the next power source comes up, like say DC set trigger up and then providing the your power, you have to ensure that the cooling should be ensured, like say whatever the gap it is, whether it is 1 minute or 2 minutes, you have to ensure that enough cooling is available. Okay, overall temperature is maintained so that it can continue the work. So this is the, like say I have the permanent, that is the interconnect, I have the InfiniBand, that is another interconnect, and I have management networking nodes, and I have this is another management IPMI, and then I have the storage, and I have the nodes, and these are the precision ACs. This is the pack. So I have 5 packs. I need at any point of time only 4. This is the n plus 1. So it does a round robin to provide the redundancy. Okay, it is not that only this pack 5 is never used, it is a round robin. And this is the battery bank for the UPS. So why I am saying all this is, there is a reason for that. Why I am saying all that, we are going to discuss in future about this, what is this particular, why I have shown you this rows, why I am saying this is the storage, why I am saying this is the storage home FS, this is a parallel file system. Then I have this UR2 nodes. Okay, then I have this another UR2 nodes, then I have this packs, I have the AC, UPS, batteries and transformer, gensets, etc. Okay. Come to the next slide. So what I have to do is, for example, if you take a CPU is working at like say 2 gigahertz or a 2.4 gigahertz or a 3 gigahertz speed. So can I have a measurement at 3 gigahertz? I cannot measure it. It's not easy to measure it, the variation of the power consumption. When the CPU is working at 2.4 gigahertz or a 3 gigahertz speed, I cannot take that many readings in a particular cycle, okay, or in a particular second. So then what I'll do, it's not second, it's actually a cycle. Now what I do is, instead of that, what I can measure is what is the frequency of the electricity or the power what I am giving to this particular facility, that is running at 50 hertz. Now I'll say that I should be able to take at least 50 readings of a one cycle. Okay. Now that means I'm able to get, like say for example, if you take a sample, I am actually getting 12,800 readings per second. Okay. So that is the kind of measurements I need it. Like say if I need to take a 12,800 readings per second, I need a different kind of meters, which are digital multimeters. Like say this model is like say LM35, like that 2-3 other models are there. So they are going to give you the harmonics measurement. They are going to give you the, what is your per second, how many readings it should take it. and it should also measure the phases, each phase. So this particular thing is the meter is used for measuring this particular number of samples. Now you see this. What is that we have used? So this equipment are called power analyzers. Okay, and each of this is the make of it, and this is the model, and this is the power analyzer. So each power analyzer, what I have done, I have connected. One is the row 2, source 1. What it means? I have 2 UPS I have shown you. So each rack is getting power from UPS 1 also and UPS 2 also, and the load is equally distributed across this UPS 1 and 2. If UPS 1 goes down, the 100% load will be taken by the UPS 2. That is how it is designed. Now what is happening? If I have to measure a particular performance or a power consumption of a particular rack, I should able to measure both source power sources, like say source 1 and source 2. Now what happens? Why to restrict only the power source 1 and source 2 only for this entire rack? I should go beyond that. I should able to also measure the power consumption by a particular node also. Right? I should able to know what is the power consumption of a particular node. I should know about entire rack, what it is consuming. I should also know entire row, how much it is consuming. And I should also know a lot of other things, like say source 1 and source 2 with respect to each of that measurements what I am talking about. Now this is how the meters are placed. You can see this. These are all connected to this power chambers. So I have a source 1 and source 2, as I told you, UPS 1 and UPS 2. And nodes are in 2 rows, like say R2 and R4. That means if I have 2 rows, that means each row is having source 1 and source 2. That means it is 4 actually measurements for me, 4 rows. Right? 4 measurements. Even if it is 2 rows, what I am doing for each row, I have to measure entire row wise R2, okay, and R4. So each row is having 8 tracks. Like say if this is the horizontal, if you take it, rows, now I'll take vertical. Now in each of the rack, it's 8 having this entire, 8 tracks are there per row. That means 16 readings I am going to get it if I go for each and every rack. Okay, in that particular entire row. Okay, or if my power source is designed such a way that each row is having a separate power coming up to that, I can measure it there also. Okay, so here in this case I have the measuring points of row 2 source 1, row 2 source 2, then row 4 source 1 and row 4 source 2. This is my placements of the server, so I need to collect that particular source 1 and source 2. Apart from that, what I should collect? I should also collect IB, that is the InfiniBand consumption. I should able to also measure the gigabit Ethernet, and ILO means management, server management board interface. Okay, and all the powers drawing with respect to that equipment. Okay, and for the source 1 and source 2. Okay, so when it comes to the singing node, when it comes to the singing node, I will connect an analyzer to a singing node. Okay, and so total we have used around, we have 4 rows. So 1 row is for entire storage. So 1 row is for the parallel file system, and another is shared file system. Then I have the compute node, another compute node. Then I have the networking equipment in between. So considering that, I need to use around 6 analyzers here to get that power source. So this I am skipping. This is like say course wise, how much it is. Now you see the lean pack. If you see the lean pack, you want to whatever we have run long back, that is around 38 TF. What is the theoretical 388 TF? Okay. What is the theoretical performance is 540 TF. Okay. So that is now what is the efficiency here? Like say performance per watt is calculated based on what is that consumed, and that gives me what is that exactly the ranking of the system. So average power what it is drawing is 220.68 kilowatt. Performance is 380 to 442 gigaflops. And plops per watt is 1.76 gigaflops per watt, which is not so great. Okay. And this is the performance what I am getting when I measure it with the power consumption. Okay. Now the question is, what are all the to be measured? Okay, what are all the to be measured is the storage consumption, the HPC interconnect consumption, then my management network consumption. I should measure it at nodes level consumption. I should measure a one particular rack. I should also measure entire row, and I should also measure one server. Okay, when I do that, then whatever I have collected, then I can see, I can correlate it and understand what really it is. Okay, like say, what is the power source? What is the total power I am using it? Okay, for this, and what is the IT power alone? For IT, how much I am spending? For all that, and apart from that, what are else I have to take it? This is only IT load I am talking about. Where I have to keep my meters again, I have to measure PACs. What is the consumption of the cooling equipment? I should also measure the losses with respect to the UPS. I should also measure losses with respect to, cooling. So I need to know cooling losses. I need to know power losses, and I should also know the consumption of each of the particular node. I should know the consumption of overall row and the rack. So these are the readings. I should take it based on the 50 heads. That is, I am taking around like say 12,800 readings per second. So these readings are plotted on a graph and then compare it with the lean pack performance, what it is giving. At that lean pack performance, what is the power consumption or overall power consumed? Then that will give me performance watt. Okay, I think this is clear. Any doubts here?
No, sir, not at posted, sir. Please proceed.
Not posted, right?
Yes, sir.
So I think this is what it is about, the green 500. And so measurement, whatever I am talking about, I should be able to measure even the harmonics. I should be able to measure the various consumptions. Then only I can get I should know the losses at the UPS. I should know the losses with respect to the power, this precision air conditioning. I should know the consumption of this. I should know the consumption of the storage. I should know consumption of the nodes. Then I can say that what is the overall power consumed for this entire, the data center divided by only the IT load. That gives me the PUE. Okay, when the PUE is high, that means your system is efficient. If the PUE is 4, then your system is not efficient. So that is how the green 500 measurements are taken. That is how this ranking has been given. Okay. So any doubts? Anybody having any doubt? So when we have measured that param, we got around Asia. If you say that Asia Pacific region, we are the 7th. And if you see the green 500 top green 500 supercomputers, I think we are at order of around 40 to 60. So that is the ranking. Okay. So if you have any doubts, please let me know.
Participants, if you have any doubts regarding this 500 and green 500 supercomputer green computing aspects, if you have anyone has any clarification, directly ask Swarup sir. No sir, actually.
Okay, ठीक है, then I am done.
Yes sir,
And
yes sir.
thank you so much. Okay.
We'll wait for a few minutes if anyone is asking, sir. Yes, sir.
Have you understood, like say, I think all this audience are understood about this, various cooling techniques, right?
Yes, sir. Yes, sir. Yes, sir.
The rack level, row level, then, then system level, the CPU level. Okay. There is another technique which is a immersion based cooling. That means the servers are kept in a particular liquid. Okay. And it gives more efficiency, but the problem is you have to change a lot of things in the server. You have to remove the fans and other things because it doesn't work in the liquid when you immerse the entire server in the liquid. Okay, there are servers which are available which can be inside they are immersed in the liquid, and that liquid is not going to give you any electrical short or anything. Okay, and that is how the heat is removed. If you go to the European countries, what happens is they are more efficient because what happens here, because of the heat, in India you have to spend a lot of cooling, right, because the outside temperature also is high. So when you go to the European countries and all, they are talking about a warm cooling, warm water cooling. What is that warm water cooling is? Because they cannot give a chilled water, right? The chilled water, what happens? The pipes will become jam because of this. They become ice. So what they do is they do a warm water. Okay, they are actually putting an extra effect in sending a warm water, and they will send the warm water at like say 20 degrees, something like that. Okay, so that is a warm water cooling, and so the immersion is one type of cooling, and warm water is another. The way they give the cooling to the system.